Let's look at problem 12 that you voted off the island. The first thing you want to do when you're faced with a messy circuit like this is to decide what's independent of what. So you've got this battery, you've got A and you've got B. And if I consider A and B as a branch, it's got direct connections to both sides of the battery. That's going to be an independent branch. I'll call that 1. Now, if I look at the rest of the circuit, it looks all messy. Now, here's the thing. When you're in an argument with someone, you never want to let them frame the debate. Similarly, you don't want me to draw your circuit for you. I'm going to draw it in such a way that's going to be as messy as possible, as confusing as possible. You want to draw the circuit to make it clear what is in parallel and series and what is independent. Okay? So if I give you this, don't stick with it. Redraw it. That's the most important skill that you'll bring with you after being able to tell which is more resistance. Now, this was C, D, E, F, and G. When I redraw something, I redraw it in such a way that the two branches are the same. So I would redraw this . That's pretty simple. Boy, don't you wish that were the circuit that Greg gave you on the exam? Yeah. I mean, the current would split 50-50 there. All these bulbs would be the same brightness. Would go on to problem 2. Now, folks, let me just pause here and point out that that problem 12 was problem 1 on an exam. When you look at the 2 sample exams, they all have a problem 1 that looks like that problem 12. There's a messy circuit. You're asked to compare bulbs 2 at a time. Then you make a change to the circuit, and you're asked what happens to some of the bulbs. That's always the first page. You can count on it being the first page of your exam. It'll just be a different circuit. Okay? Now, once you've drawn the 2 branches identical to each other, you ask yourself, what's missing? Well, the only thing missing is C, D, and E. And I add them on a separate new path, like that. Now, it doesn't matter what I add. What's important is that I added it in parallel as a new opportunity for flow. Now, the first bulbs that you're asked to compare in that problem are A and G. A is an indicator for branch 1. All the current through branch 1 goes through A. G is an indicator for branch 2. All of the current through branch 2 goes through G. So what I'm really asking is, how does the current split here and then come back together there? Which is the easy path and which is the hard path? Now, many of you are going to just say, oh, that's the easy path, that's the hard path. But on an exam, you have to justify that answer. This is what I would expect for a full point answer. I would say, branch 2 is the same as branch 1, except for the extra path with C, D, and E. Therefore, the resistance of 2 is less than the resistance of 1. By V equals IR, the current through 2 is going to be greater than the current through 1. And the last step would be A and G are indicators for their branches. Now, if you left off that last step, we'd probably give you full credit, just assuming that that was obvious to you. But that would be a perfect answer right there. Now, the next one that you were asked to compare are A and B. And they're equal, and all you have to say there is series. So you see, you got to say more words for that other set. Okay, I forgot where we're going from there.
C and F.
I'm sorry?
C and F.
C and F? Okay. If I'm comparing C and F, I'm essentially asking how does the current split there and come back together there? Well, I've got a hard path and an easy path, and this is the hard path, this is the easy path. To tell which is the hard path, I circle the new stuff. D and E. If it weren't for D and E, the current would split 50-50 here and come back together there. And then I asked, how did I add D and E? Now, D and E are a parallel network, but that's not what I'm asking. I'm asking, how did I add it? And I added it in series. I had to use scissors to put that in. If I look at Fred on his journey, Fred can go through one bulb and be back to the mainland. Here, Fred goes through one bulb, not back yet, got to go through something else. It might be an easy something else, but it's still something else. So I would say that F is brighter than C, and my reasoning is current favors path of least resistance. My students were using that path of least resistance for I think a year and a half before I figured out what it meant. I thought it had to do with Santa Claus. But path of least resistance, okay? Polar. Now the next two are
G and F.
G and F?
Yeah.
This is an all versus part argument. You could say G is the indicator for branch 2. It gets all of the current through branch 2. F only gets part. The other way to do it mathematically is to say the current through G is equal to the current through F plus the current through C. Okay? Those two paths all go through G. Now the last one, B versus F. Is that right?
Yes.
Okay. That one is a pizza problem. B gets all of the small pizza, F gets more than half of the large pizza. So that means that I have to pick a path that goes through B and pick a path that goes through F, and I set those equal to each other. If I want to compare B and F, I first of all have to compare the other two. I've already compared the other two. That was the first thing I did up there. And I said, oops, I didn't say, that G is brighter than A. Well, if G is brighter than A, then it's got more volts across it than A. So now when I compare the other two, the inequality has to go the other way. And so B is brighter than F.
So I have a question for you. As it's drawn there, is the path through F and G not independent to the rest of the circuit? Because there's a path directly to the battery that doesn't have to go through anything else. It can only go, it could go through just F and G, so that has to equal V battery. Is that correct or incorrect?
You're saying would that be independent?
Well, meaning that if I measured from the top F to the bottom of G, would that not have to equal V battery?
That is, yeah.
So-
F and G have to be 12 volts.
Okay, same with A and B then.
Same as A and B.
Okay, so we have to mix and match the models to determine something? Is that essentially what you're saying? 'Cause if you use the voltage model, by what we just said there, then A, B, F, and G would be equal.
Oh, heck no.
No, because of the
No,
current model.
all I know is that this has to add up to, these guys have to add up to 12 volts,
Okay,
and they're in series. So there's 6 volts and 6 volts. These guys add up to 12 volts, but they are not in series. Everything that goes through G doesn't have to go through F.
okay.
What is in series is G and this network,
Okay.
all of that.
So, yeah, essentially what we're doing is for different comparisons, we can use the current model for some, we can use the voltage model for others.
And typically people start with the current model because they spend more time with it. When they get stuck with a pizza problem, they go over to the voltage. But if voltage is more comfortable for you, you can just start with the voltage model and switch when you get stuck.
So are we saying that G would have greater than 6 volts?
Yes.
Okay.
G has greater than 6 volts, and F would have less than 6 volts. Okay? Now, in the last part of this problem, we take out bulb C and leave the empty socket behind. That's just a gaping hole. Now, after I take out bulb C, F and G are in series. Because now everything that goes through G has to go through F. There's no longer a path going through the other way. And now, F is going to change from less than 6 volts to 6 volts. It's going to get brighter. G is going to change from greater than 6 volts to 6 volts. It's going to get dimmer. And B is going to stay 6 volts. It will stay the same. Okay? Check that your neighbor's on the bus with this. We also have a solution at the D2L site